Welcome back. The team has identified a potentially attractive prospect. There is a producing source rock, the pathways followed by the hydrocarbons have been predicted, and the reservoir defined. A geologic model will be developed which forms the basis to estimate the expected hydrocarbon volumes and the probability of success, POS, which is the likelihood that the well will encounter producible hydrocarbons. Worldwide, only about 40% of all exploration wells is successful. Never forget that uncertainties associated with subsurface predictions are always large. Estimates are therefore always given with reliability ranges. With a convincing model and these estimates, the team will propose to the management to drill a well. The moment of truth has come. The borehole has traversed an effective seal, has then reached the target reservoir, which turns out to have an important effective porosity. Oil and or gas have appeared, showing that the hydrocarbon play is functioning. Gas or oil will flow into the borehole and form a column higher than the top of the reservoir. This documents the permeability and pressures of the reservoir. The well has been a success and has confirmed the model prepared. The team is now confident it has a good case for the management. The company approves the plan. Activities become hectic. New seismic data is acquired. New wells are drilled. The goal of these studies is to provide a detailed geologic model of the reservoir, inclusive of the hydrocarbon present and of the geomechanical characteristics of the system, and an estimate of the reserves, producible volume of hydrocarbons of the reservoir. Geologists are not the only ones being busy during this stage. Engineers start envisaging the infrastructure needed to extract the hydrocarbon and to bring it to the market. Economists start calculating the cost of the entire operations and compare it with potential revenues. All these numbers, geologically and not, need to be associated with uncertainties. These are a fundamental part of the decision-making process. Analyzing seismic data and wells, the geologists will interpret contacts between formation and faults. These features determine the architecture of the model. One of the main uncertainties associated with this stage is the accurate translation and depth of the seismic signal, which needs a knowledge of the velocity of the rocks. The following step is to define the sedimentological properties of the reservoirs. Because good reservoirs are characterized by good permeability, this is equivalent to predicting the distribution of sands. This is an easy exercise if the rocks are homogeneous. If not, then the different heterogeneities must be included in the model. As information is only available from wells at a very small scale and at a much larger scale from seismic, the data needs to be interpolated. The next step is to predict physical properties, such as porosity and permeability. Also, this step has large uncertainties. Real information will be very scarce and essentially limited to the cores and cuttings from the few wells which have been already drilled. Interpolation between data points is done typically according to stochastic protocols, steered by the geological knowledge of the operator. These models again contain large uncertainties, which are quantified and translated in risks. Zooming into the model, you see that this is discretized in small volumes called the grid cells. Properties are assigned to each of these cells and calculations are done with them. The size of the cells controls the spatial resolution of the model. Models currently use millions of cells for their calculations. Despite these amazing improvements, you must realize that a normal cell corresponds in reality to a tens of meters, and therefore each cell contains large heterogeneities. In the previous slides, we have looked at reservoir where the porosity is associated with sedimentary processes. In fracture reservoirs, permeability is controlled by the distribution of fractures. Models are created predicting the distribution and geometry of these fractures. In the slide, predicted fractures are all the thin black lines. As you think that only control points are the boreholes, you can imagine how full with uncertainty this process is. Adopting the model geometry and assigning physical parameters such as rock strength, intensity of stresses, etc., Geologists may also prepare a geomechanic model which geoengineers will use to plan their drilling strategy. Until now, the team has defined the properties of the reservoir, but what is inside it? One of the key parameters is the position of the contact between the water below and the oil or gas above. In the case shown in the slide, the reservoir in the left side of the picture is filled with water. Oil is only present in the central portions, indicated with the green colors. At this stage, the team is ready to estimate the amount of oil and or gas present in the reservoir. This is called the standard tank oil in place, STOIP. This number corresponds to the volume of the reservoir corrected for a number of factors shown in the slide. STOIP is obviously an important number, but the key question is how much of this can be recovered and at what costs? The answer to this question is not only related to geology but also to economics. Even in the simplest reservoir, drilling more wells will allow accessing large part of the hydrocarbons. And maybe it would be preferable to drill horizontal wells. In addition, a strategic plan must be made deciding how fast one wants to empty the field. Key for answering these questions are numerical flow simulations. These simulations start from a simplified version of a geologic model and integrate the fluids present to the system, water, oil, and gas. One or more wells is drilled through the system, and the numerical code simulates the flow of fluids from the reservoir to the well itself. These simulations must take into account a large variety of complex phenomena such as thermal expansion, pressure changes, wettability, changes in porosity, and much more. Flow simulations in real-world reservoirs are among the most challenging experiments in the world. Your job as a geologist might have finished, but engineers and economists are working hard to develop the best scenario and to make sure that production is cost-effective. Having hydrocarbons in the reservoir is of no need unless it is brought, the hydrocarbon is brought to the surface and sold. Studies are now finished. A production plan has been established, infrastructure has been built, the field can be brought into production. Your work as a geoscientist, however, is not finished. You will make sure that the huge amount of data being gathered during production is used to update the geologic model. Your knowledge will be necessary to plan wells, maximizing production and minimizing risks. And when reservoir production will start to decline, you will have an important role in designing new interventions to extract more of the petroleum locked into the rock. Steam injection, water flooding, gas injection, plenty of challenges ahead.